Hey guys, welcome to lecture number 11. So in this lecture, we will be starting something new. We will be talking about, we'll start basically the real analysis. You will see, and from this point on, we will be talking only about real analysis. So we will cover topics such as sequences and a series of real numbers. And in fact, I will devote two separate lectures, one to sequences of real numbers and the other one to series of real numbers. Then we will start talking about limits and continuity, then differentiability, then integrals, and then some multivariable calculus. And then at the end, probably this will go beyond the semester. Maybe I'll record a video about differential equations as well, so that we can have the whole package. But today we will talk about sequences of real numbers, and next week we'll separately be talking about a series of real numbers. So let's get started. All right. Now let me just say a few things about sequences of real numbers. And so sequences of real numbers. Usually, you learn about this stuff more in detail in a Math 4351 here at Tech. I taught this class. This is considered to be the most advanced. Well, actually, no, it's Math 4350, and I taught Math 4351, which is the second part. So this is when you learn more in detail about this stuff. And right, what we're interested here, and I'm not gonna maybe the definition. I'm not gonna tell you the definition of a sequence, but you know what a sequence is. So basically, when you have n greater or equal than 1, right? It's a function that from the set of positive integers to the real numbers, right? So you can only take values here for n equals 1, n equals 2, n equals 3, and so on. Okay, and what we're interested in, so this is the sequence. So this is a sequence, right? Let's say, okay, let me just say, it's obviously, so this is the sequence, right? This guy here. And what we're interested in here is this word, which we call convergence. Right? So convergence, and eventually we will be interested in finding the limit. So what is the limit as n approaches infinity of an, right? So these are the two words that we would like to take care of. And there are plenty of ways. Let me just remind you, the definition of the sequence of real numbers. So basically, we say that the sequence, the definition of the convergence, right? Let me just write it here. So xn, okay, I'm gonna write it here. Xn converges to, let's say, L, a real number L, if for all n, right, there exists an n epsilon, right, such that for all n greater than n epsilon, we will have that xn minus L is less than epsilon. That's that's the definition, basically. So in other words, you say that the sequence xn converges to a number if the sequence contains all the terms of the if the number L, sorry, contains So all the terms of the sequence are in the neighborhood of L, excepting a finite number of them. Basically, you can throw out a finite number of them, and the rest will stay there. So that's what this is what they mean by convergence. And now we would like to see what do we mean by the limit. So what is this guy here? So how can we find the limit of M? And there is a so-called, so I'm going to jump directly into some more stuff. And there is this theorem, which we'll call the monotone convergence theorem. Which says the following. It says that any monotone and bounded sequence, right? Monotone and bounded is convergent. So that's what you need to know. In other words, here I should say that any monotone sequence has a limit, finite or not, right? It can be infinite as well, but definitely, so let me just say here, so any monotone sequence has a limit. Finite or not. Okay. But moreover, if the sequence is bounded, then you can definitely say it's convergent. And moreover, if the sequence is convergent, then the limit is finite. All right, let me give you some quick examples here. In fact, I'll show you some other tools as well. So examples of sequences. And the first one that I have in mind is the nth root of n. And let me just say here for n greater or equal than 1. Right? Well, with the convention that the one root with the convention that x1 is 1. Well, for n equals 2, let me just, we have this x2 is square root of 2, n equals 3, x3 is cube root of 3, and we keep going. Let's say n equals 4, x4 is 4 root of 4, which is square root of 2, n equals 5. We have x5, and we keep going, right? Well, you can observe something here, if you look at it, that this term is actually the greatest term. So the sequence increases, so this is what happens. x1 is less than x2, is less than this guy here, x3. This is, but then something even happens, so is greater than x4, greater than x5, and so on. So what does this mean? So this means that from the first term all the way up to the third term, the sequence is increasing. So from here to here, xn is increasing. And from here to here, xn is decreasing. Right? Okay, so the sequence is decreasing. All right. Well, in fact, we can say even more that the sequence actually converges. So the sequence xn converges to 1. And there are plenty of ways to see this. Well, let me show you. Well, let me show you a tricky way. And I would like you to keep this idea in mind, because we will use this idea next week when we will be talking about series of real numbers, and you'll see that well, solve a problem. In fact, it's one of my favorite Putnam problems, and you will see how this idea will come into play. But anyway, let's see why this guy converges to 1. And I would like to use what we'll call the squeeze theorem. And let me show you a magic trick. So look at this guy. So I have here the n root of n, which is greater than 1. That's obvious. But this guy here is the n root of, so I can say 1 times 1 times 1 times n. And here I have n minus 1 times, right? And here, by applying the AM-GM inequality, I'll have that this is less than 1 plus 1 plus 1 n minus 1 times, so, right? So I have here n minus 1 terms plus n, everything over n. And if you look at this guy, let me just, so if you look at this guy, this is, what do we get here? We have 2n minus 1 over n. So this 1 will converge to 1 as n approaches infinity. And this guy will converge to what? Can you tell me? 2n minus 1 over n as n approaches infinity converges to what?
2.
2. Look, what do we have here? We have a gap. We have a gap here. So this means that the squeeze doesn't work the way we want it. So maybe we should do something. You see, the problem is that I have an extra n here. So I have n to the power 1. So now the trick is to break this into smaller powers. So how can you break 1? Well, you can break it any way you want, but one way to do it is just to what? To write 1 as 1/2 plus 1/2, right? So let's do that. Now let me erase this now. I want to squeeze that gap, and I'm going to do the following magic trick. Ouch. Something happened with my Zoom. Give me 1 second. Okay. All right. So unexpectedly, they announced me that something, anyway. All right. Now let's look at this guy. And now I'm just going to write here, I'm going to write square root of n times square root of n. And here I'll have n minus 2 terms. All right, now since I have this will be 1 plus 1 plus 1, n minus 2 times plus 2 square root of n, everything over n, which is equal to n minus 2 plus 2 square root of n, everything over n. And now this guy will converge to what? Can you tell me? Does it converge to 1? Yes, it does, right? So this will converge to 1. And finally, by the squeeze theorem, this will converge to 1. Right. So by the squeeze theorem, xn converges to 1. All right, basically I just showed you the limit of this, right? That xn converges. So the limit as n approaches infinity of the n root of n is 1. But now well, I just jumped a bit forward and I just said a few things about the limit of this, but maybe I could say something about what about the monotonicity, right? Well, if you look at the monotonicity, maybe I should have said something about that in the first place. The sequence is decreasing. So, and I'll leave this to you as an exercise. So the sequence xn is decreasing. basically what we did in the first place is not quite a proof, it's just an exploration, if you want. We basically just look at the terms of the sequence, and we can make some assumptions about how the terms will behave, but that's not quite a proof. So xn is decreasing for all n greater or equal than 3, and this is to use an exercise. Anyway, it's quite easy to see. Okay, this is the first sequence, so the first example, 1. Now let me see the second example, and the second example will be related to this, and this is what we call En 1 plus 1 over n to the power n greater or equal than 1. This is what we call Euler's sequence, and this will be very important because we'll deduce a bunch of things here. Okay. Euler sequence. What do we know about this guy? So we know that this guy is increasing. So En is increasing. Moreover, An is bounded. It's between 2 and 3. One can prove this. Anyway, I'm not going to prove it. And well, from the monotone convergence theorem, so monotone convergence theorem, so MCT, I'm going to write it like this. I'm going to abbreviate it by this. It will imply that An will converge, and moreover will converge to this guy E. And this guy is 2.71, and you keep going. E is this irrational number. Moreover, it's transcendental. It's not even algebraic. Right. And now we can point out a remark. So since En converges to En, En is increasing, it follows that En is actually less than E, right? So that's what we need to know. But in a similar fashion, so similarly, one can consider the sequence, and I'm going to tweak a bit this guy En. So this will be Fn will be 1 plus 1 over n to the power n plus 1 for n greater or equal than 1. The same thing happens here. So Fn is decreasing this time. So that is the main difference between the two. Okay, let me stress this out. Again, Fn is bounded. And well, of course, by the monotone convergence theorem, Fn will converge to what as n approaches infinity? So Fn is convergent, and moreover, it will converge to, can you tell me?
Is it 0?
No, look at it.
E.
E.
Right.
Because it's it's En times 1 plus 1 over n, and 1 plus 1 over n converges to 1. All right, but now, moreover, we have this thing. So moreover, since Fn converges to En, Fn is decreasing, Fn will be greater than E. So we have the following. Let me write the double inequality. So we have E here, and we have this between, this is 1 plus 1 over n to the power n plus 1, and this is 1 plus 1 over n to the power n. Look at this guy. This is one of the first inequalities that you need to take into account. And now, what I'm going to do is take the log, so apply the log, natural log, ln, or usually ln for me is also log n, so that you keep this in mind. And once you do this, it will follow the following inequality, and I'm just jumping through details. I don't want to do the computations. Ln of n plus 1 minus ln of n is less than 1 over n and greater than 1 over n plus 1. So we'll have this inequality for all n greater or equal than 1, if you want 1, 2, anyway. So this is a very important inequality, and you'll see we'll deduce some things. And the first thing I want to deduce is the third sequence. The third example that I want to do is the harmonic sequence. Hn is 1 plus 1/2 plus 1/3 plus so on plus 1 over n. So this is what we call the harmonic sequence. Right? Well, what can you tell me about this sequence? Do you think it does this sequence converge or something like that? Diverge? What do you think? What does your yes?
Convergence?
Converges. Your intuition will say that this is actually convergent, right? You'll be tempted to say this. Okay.
Yes.
But okay, so basically you have 1, you have 1/2, 1/3, and you add less and less and less and less. So you'll be thinking, well, at some point it will be around a finite number, right? Whatever that number is. But unfortunately, this doesn't happen. The sequence actually diverges. I know it's kind of counterintuitive, but this is what actually happens. Anyway. Let's see why this is true. Look at the inequality above. That's why I just left it there so that you can see it. You see, you have 1 over n, and if you look at this 1 over n here, right? Look at it. If you look at 1 over n, so we know that one over k, let's say, is greater than ln of k plus 1 minus ln of k, for all k greater or equal than 1. So now you can just put there k equals 1, k equals 2. So now it will follow that 1 is greater than ln of 2 minus ln of 1, k equals 2. It follows that 1/2 is greater than ln of 3 minus ln of 2. And we keep going, right? Let's say k, let's put here n minus 1. We have 1 over n minus 1 plus greater strictly than ln of, so k, ln of n minus ln of n minus 1. And let's say put here the last one so that you can see it better. It's 1 over n greater than ln of n plus 1 minus ln of n. Right? Okay. And if you add all this, add up everything, what do we obtain? Can you tell me? What do we get if you add up everything? You see, when you add up everything, you'll have Hn greater than. Now look at these guys, how they go away. This with this, right? This will move something like here. This with this, and this with something here. The only terms that remain is the last one and the first one. But the first one is 0, so it will be greater than ln of n plus 1. And as far as I'm concerned, ln of n plus 1 as n approaches infinity will converge to what?
Infinity.
Infinity will converge, will diverge, sorry. So Hn will diverge to infinity. Right? So Hn is divergent. Okay, that's beautiful. But now, don't be just happy with the fact that Hn diverges to infinity. We can actually see even more. If you apply the other inequality, right, because there is a double inequality. So moreover, we have that that what? That Hn is greater than ln of n plus 1, but more is less than what? Than 1 plus ln of n. And now you can see what order of magnitude has this sequence, whatever that means. So basically it behaves like ln of n. In other words, Hn over ln of n, the limit as n approaches infinity. So from here, so it follows that by the Squeeze theorem. So let me write here Squeeze theorem. That Hn over ln of n is between, well, here we have ln of n plus 1 over ln of n. And this is 1 plus 1 over ln of n. And I'll leave this to you as an exercise to show that this converges to 1 and this will converge to 1. And by the Squeeze theorem, this will converge to 1 as n approaches infinity. Right? Okay. So now we know a couple of things about the harmonic sequence. Well, there's plenty of other things to say. I think I gave a talk at the what is it called? The MATCOB. Well, I talked about the harmonic sequence and even about the fact that it is related to an elementary problem equivalent to the Riemann hypothesis. Anyway, I actually have in fact, I gave 2 talks. One of them was at Pitt, the other one was here at TTU, and they're on my channel. So if you want to look them up to see what's going on, anyway, you can go there. Now, there are some other things that I would like to talk about. Okay, maybe another sequence, maybe we can tweak this a bit. Because here I would like to to say some things about another sequence. What if we have the sequence gamma n is Hn minus ln of n? Right? We can prove that, and I'll leave it to you as an exercise, that gamma n is decreasing, that gamma n is bounded, is between 0 and 1. So again, by the monotone convergence theorem, gamma n will converge to this constant gamma, so approximately 0.77 whatever. And unfortunately here we don't know anything about gamma. So let me just say here gamma is what we call Euler-Mascheroni constant. And it's a mystery. We don't know anything. We don't know if it's irrational. We don't know. Definitely we don't know if this is transcendental, nothing. So. And from here, one can deduce the following. And let's do a couple of in fact, I'll leave, so let me say this as an exercise. From this sequence, one can prove that the limit as n approaches infinity as of this sum is ln of 2. But I would like you to think a bit of this problem. So let's see, who is this guy? If you look at it, this guy here. Well, if you write this is nothing else than 1 over n plus 1 plus 1 over n plus 2 plus 1 over n plus n. Right? Do you see something about this sequence? Does it is it related to something? What do you think? Let me be specific. Is it related to the harmonic sequence? Can you write it in a certain way? Well, isn't it just h2n minus hn? Right, because h2n is 1 plus 1/2 plus all the way 1 over n plus 1 over n plus 1, 1 over n plus 2, all the way to 1 over 2n, right? So that's what it is. And now we're going to write it in the following way. So let me just denote this by an. So an can be written in the following way. So let me show you something. hn minus ln of 2n minus hn minus ln of n. And let's see now, I have to add ln of 2n and subtract ln of n. So ln of 2n minus ln of n. And this guy here, this is just ln of 2. And this guy, look at these two guys. This will converge to what? As n approaches infinity. This will converge to gamma because it's a subsequence, right? This is gamma, this is nothing else, this sequence here. This guy is nothing else than just gamma sub 2n. This is gamma n. And of course, this will converge to gamma as well. So have gamma minus gamma plus ln of 2, which is indeed. So an will converge to ln of 2 as n approaches infinity. Right? Is it clear for everybody what I'm saying? Gabriel, is it clear?
Yeah, is, so. Oh, okay, never mind. Yeah, I get what you're doing.
Okay. Okay. Guys, Timothy, Chris.
Yeah, I'm good.
Okay, that's good.
I'm good.
All right, so
I see it.
keep this in mind. We're going to use it at some point in one of the problems because I want to give you an example of how to compute the limit of a sequence using the squeeze theorem. And in fact, once I'll give you the homework, you will see some other problems for Thursday, which will be similar to this. But anyway, let me go. Well, let me just mention one more thing, and then I will jump directly into solving problems. And this is what we will call, okay, let me say it as a theorem, but usually it's called the Cesaro-Stolz lemma. Right? Well, if you want, this is nothing else than just L'Hopital. You will learn this, and we'll be talking about L'Hopital rule, the discrete version. And you'll see what do I mean by that. Okay, now so we have two sequences, an and bn, right? Let's say a and bn are positive, contain only positive terms, right? And such that, so let a and bn, such that the following conditions are true. The first one, an is increasing and unbounded. And the second one, the limit as n approaches infinity of Bn is infinity, right? And the third condition, which is important, let me write it with a different color. There exists the limit as n approaches infinity of an plus 1 minus an over bn plus 1 minus bn. And this guy will be in R bar, which will be R. This is nothing, and we, with these two elements, plus minus infinity. But in our case, it will be just infinity, but anyway. So the theorem says that then, I'm going to write it like this, there exists the limit as n approaches infinity of an over bn equals L. You see, this guy here, if I want to look at it, this is nothing else. This guy, an plus 1 minus an, this is, we will call this delta an, which is the discrete derivative of an, and this guy is delta bn, which is the discrete derivative, if you want to put it like this. Discrete derivative. Remember L'Hopital rule? The limit of f over g is the same as the limit of f prime over g prime. So the same here. The limit of an over bn is the limit of delta an over delta bn. So the derivative, the discrete derivative of an over the discrete derivative of bn. I don't know, for some reason, this lemma is overlooked in American textbooks, and I don't understand why, because it's very, very useful, especially when you deal with sequences of real numbers. And I'll show you some examples. All right, so this is the Cesaro-Stolz, and now let's see some problems. And the first problem I have in mind is the following. Let me show you some examples. Problem 1. This was a Putnam H3 in 1966. So 66, yeah, something like this. And the problem says the following. Now it's a pretty classical problem. Let xn, n greater or equal than 0, be a sequence such that the first term x naught is between 0 and 1, and xn plus 1 is xn times 1 minus xn, for all n greater or equal than 0. The first thing is to show that xn is convergent, and the limit as n approaches infinity of nxn is 1. Okay, I want you to look at this problem for a bit. So how would you approach this problem? You see, this is what we call a recursion. When you look at this problem, you see you have this xm. Look at this recursion here. So xm plus 1 So let me just point out something. So xm plus 1 is, let's say, a function, but I don't want to do all too much on this, of xn, where this function, f of x, is x times 1 minus x. And of course, you can study and x is between 0 and 1, let's say, and you can study the behavior of this function if you want. You can find the min, the max, whatever. But what is the first thing that comes into your mind? You see, you have this information here. Look at this here. So once you know that the first term is between 0 and 1, maybe you should prove what?
It decreases.
Even before that,
It's bounded.
it's bounded, right? So you see, when you have this information that x naught is between 0 and 1, maybe you should prove. So, and I'll leave it to you. So by an easy induction, we can prove that xn is between 0 and 1. So it is in this interval. Why is this for all n greater or equal than 0? Why is this true? Well, if you look at it, just look at it. If you look at this guy, right? The first term for n equals 0, it's clear. But if you look at the recursion, this guy, so assuming that xn is between 0 and 1, clearly xn times 1 minus xn will be between 0 and 1. So by induction, so it will follow that xn plus 1 is between 0 and 1. So by the induction principle, it will follow that xn is between 0 and 1. Is it clear? What am I saying here? For everybody? Right? Okay, I'll leave this to you as an exercise. Put it here. All right, so xn is bounded. Great. Moreover, just like Jack said, xn plus 1 minus xn is nothing else than just negative xn squared. But this guy is negative for all n greater or equal than 0. So xn is decreasing. This sequence is decreasing. So by the monotone convergence theorem, so by MCT, all right, by the monotone convergence theorem, it follows that oh my, just give me 1 second. Just wait, just give me 1 second. All right, let's get back to our ouch. Let me just give me 1 second to share the ouch. All right, so let's get back to our sequence. Sorry about that. So like I was saying, by the monotone convergence theorem, it follows that xn is convergent. And moreover, the limit, there exists the limit as n approaches infinity of xn equals L. And this L is between 0 and 1, but closed interval. So if the sequence is between 0 and 1, then the limit can also take those values, 0 and 1, right? So keep that in mind. So now the question is, how do we find the limit of this sequence? Can you tell me? So by just passing to the limit in the recursion. So passing to the limit in the recursion. In the recursion, what do we have? We obtain, and let's see, what do we obtain? So we obtain that what? Look at the recursion. So what is the limit as n approaches infinity of xn plus 1? It is what? Is L. So we obtain L equals L times 1 minus L. And if you want to look here, it's this, it will give us L equals 0. It's pretty simple to see. So the limit as n approaches infinity of xn is 0. All right. What about the limit of nxn? So we're interested in finding this limit. So now the question is, what about the lim as n approaches infinity of nxn? You see, the indeterminate here is infinity times 0. So let's see, how do we find this limit? So this is the indeterminate here, infinity times 0. Well, we can do, well, I won't say a magic trick, but anyway, so we have that. Let me show you a technique that the limit as n approaches infinity of nxn. So again, like I said, the indeterminate here is infinity over infinity times 0, but I would like to transform this into infinity over infinity. So what I'm going to do is the following. This is the lim as n approaches infinity of, and check this one out, n over 1 over xn. So at this point, this is infinity over infinity. Let me write it here like this. But now I can apply the Cesaro-Stolz lemma. Right? And this would be equal to the limit as n approaches infinity of n plus 1 minus n over 1 over x plus xn plus 1 minus 1 over xn, right? And this would be further equal to the limit as n approaches infinity of 1 over x, xn plus 1 is 1 over, so I'm just now gonna replace xn plus 1 by the recursion minus 1 over xn. And this would be equal with the limit as n approaches infinity of, and now let's do some algebra here. So this will have, and I want you to pay attention, I can factor here 1 over xn, and this is 1 over x minus 1. And now this would be xn over, and now let's do some computations here. So this would be 1 minus xn, and here it's 1 minus xn, which will be the limit as n approaches infinity of, this is xn plus 1 over xn, right? But now, if I want to go with the recursion, right? This is the lim, so using the recursion again, this is the limit as n approaches infinity of xn times 1 minus xn, everything over xn, which will be nothing else, so these two will go away, equal that, it will be equal to the limit as n approaches infinity of 1 minus xn, which will be 1 minus L, which will be 1. And that's it. Does this make sense?
Yep.
Okay, so that's a thing. And now let me do another problem. I think probably I'll go over time, but anyway, you'll forgive me about this. Let's see, problem 2. Another Putnam problem. It was a Putnam B4 this time in 2012. And the problem says the following. It says that, so let an, I think n greater than 0, let me see. Anyway, greater than 1 doesn't really matter. With a1 positive and an plus 1 is nothing else than just an plus e to the negative an, for all greater than 1. Study the convergence of an. No, in fact, no, it wasn't like that. No. Let me just state it the way it was. Does the sequence an minus ln of n have a finite limit or not? What is it? This is how it was stated. Look at the problem. So this guy here is negative. Let me. Okay, so this is the recursion. Well, as you can see here, you're asked about this limit. You see, about this sequence here. But before you even go and talk about that sequence, maybe you should study. So first, we need to study the convergence of an. So first, we study the convergence of an. What do you think? Do you think the sequence an is convergent or not, based on the statement of the problem? What does your intuition tell you? Maybe it's not convergent, right? So let's see. First of all, it's quite clear. So by an easy induction again, we can prove that an is greater than 0 for all n. Right, again, so we'll leave this to you as an exercise to show it. It's pretty straightforward. It's just n equals 1, you have a1. Right, you assume that an is positive, then you show that an plus 1 is positive, but an plus 1 is an plus e to the negative an. So n, you know that is positive by the induction hypothesis, and then you know that e to the negative an is again positive, right? It's just 1 over e to the an. Anyway, the exponential is always positive, so it follows that an plus 1 is positive. So the induction works, and then it follows that by the induction procedure that an is positive for all n, right? I hope this is clear. Anyway, I'll leave these details to you. Basically, I just told you how you prove it, but I'll leave the details to you. All right, so n is positive. Moreover, it's quite clear that if you look at an plus 1 minus an, is nothing else than just e to the negative an. But this is positive, so an is increasing. All right, that's beautiful. Well, what do you think? We're basically on the verge. You know that n is increasing, so definitely can say it has a lower bound. But what about an upper bound? Do you think this guy will have an upper bound? What do you think? What do you think? Well, maybe it doesn't. So let's assume by contradiction that an is bounded. Again, by the monotone convergence theorem, it follows that xn is convergent. Right? Okay, so xn is convergent. And now, and the limit, let's say, as n approaches infinity of an is L. So this L will be a non-negative number. All right. So by passing to the limit in the recursion, so this implies that what? You look at the recursion, so you have L equals L plus e to the negative L. So it will follow that L is what? E to the negative L is 0, so L is infinity. Contradiction. Because we assume that this is L is finite, right? So false. So xn is not convergent. And the limit as n approaches infinity of Jesus, not xn, this is an, sorry, oh my. The same here. And the limit of n is positive infinity. Okay, so the sequence is divergent, but now look let me go back. We're interested to find what happens to this one here. Okay, so we have infinity minus infinity, so maybe we should do something, a magic trick to turn it into something. So what should we do? And here comes the magic trick into play. So we have that an minus ln of n is the same as ln, look at this guy here, of e to the power an minus ln of n. And now this would be nothing else than just ln of e to the power an over n. Right? And now we would like to compute the limit of that thing inside. So we compute now the limit as n approaches infinity of e to the an over n. Well, this guy, if you look, it's infinity over infinity. So we can apply here the Cesaro-Stolz lemma. And this will be the lim equal to the lim as n approaches infinity of e to the power an plus 1 minus e to the an over n plus 1 minus n, which will be equal to, and the lim as n approaches infinity of e to the an plus 1 minus e to the an. Right? And now, maybe we should do something. Maybe we can, well, what can we do? So this would be equal to the lim as n approaches infinity of, you see, we have this now. Maybe we can factor something. Let me factor e to the an times e to the power an plus 1 minus an, right? Minus 1. Right? But this guy here, this will be, if we look at we go back to the recursion, this would be e to the an times e to the negative, sorry. Wait, an plus 1 minus an is what? Is e to the negative an. So this will be e to the negative an minus 1. All right. But now I'm going to do something. Now denote the sequence e to the negative an by bn. What can you tell me about bn? Bn, is it will converge to what? What is the limit of bn?
Is it 0?
It's 0, correct. Bn converges to 0. Right? So this will converge to 0. All right. But now let me just, so we have that the limit, and I'm going to write it in the following way: as n approaches infinity of e to the power an, right? In fact, this is what? It's, can you tell me what e to the power n is in terms of bn? Okay, let me write it. And then you'll tell me. Oops, sorry. So this will be what? So I want to change the notation. So the limit as n approaches infinity of, so e to the, this would be 1 over bn, right? Times e to the bn minus 1. Or if you want, we can write this in the following way: as e to the bn minus 1 over bn. As, keep in mind, as bn converges to 0. This is important for you to know. That's not 0 factorial. Just, okay, maybe I shouldn't put this. But now something happens here. This is 1. And why this is 1? And let me explain it. Well, this is more like a limit of functions. So lim as x approaches 0 of e to the x minus 1, and we'll discuss this, is 1. Or if you want, lim as n approaches, you can have even a sequence xn, right, of e to the xn minus 1 over xn is 1. So you can have both, right? You can say, and this is what happens here. So the same thing happens here. It's because of this. And now, are we done? You see, what did we compute? We compute this limit here. You see this one here. But we have the log of this. So it follows that, finally, you know that the limit of the log is the log of the limit. So using that, it follows that the sequence an minus ln of n is convergent. Right? And moreover, the limit of this is what? Can you tell me? What is the limit of an minus ln of n? Is what? Is ln of 1, which is 0. And we're done. Does it make sense? All right, guys. I wanted to do one more problem, but I think I'm going to stop here. Well, probably that problem or a similar one, I'll do it on Thursday on recitation. The worksheet will be available to you as well. There'll be 40 problems there because we're going to cover basically everything. Okay, I'm going to stop here. Thank you.